we are going to solve this question. The diagram shows the drawbridge inclined at an angle of theta to the horizontal where theta lie between 0 and 90. The drawbridge is modeled as a uniform rod of weight 8,000 Newton. A horizontal force of magnitude 6,000 Newton is applied at the top of the bridge. Given that the bridge is rising, prove that tan theta is greater than 2/3. Well, if you look at the question, we've been given a hint. It says the bridge is modeled as a uniform rod, so its weight at the midpoint. So if you look at the diagram as illustrated, as I put in the blue lines, you can see for sure the rod as it is, classified as a uniform rod. It makes an angle theta to the horizontal. Okay, so what do? That is how I categorize it. I said to prove that tan theta is greater than 3/2. Let's first of all analyze the problem using the principles of equilibrium and torque. So I'll put them into steps. The step one, we have to define the system, in process. So the drawbridge is inclined at the angle theta to the horizontal. So you see, so it lies between 0 and 90. Then we model it as being given as a uniform rod of weight 8,000 Newton. So its weight acts on the midpoint of the rod. Okay, so it acts at the midpoint of the rod. Okay, so now the horizontal force given, F is 6,000 Newton, is applied at the top. You see, 6,000 Newton is lesser than 8,000 Newton, which is acting at the middle point. So now the step two, what do? We have to also see that the forces acting upon the bridge, the weight, W, is given as 8,000 Newton, as we saw earlier, acting vertically downwards at the midpoint. The horizontal force F, 6,000 Newton, applied at the top. Now, look at what I've written here. Reaction forces at the hinge, unknown and not required directly for the torque calculation. Have you seen that? That is very important aspect that you have to be able to ascertain before you be able to go forward. Now, the step three. Step three, we got to set the torque equations to be able to solve the question. Okay, so to provide inequality, take moments into bracket open and close torques about the hinge point where the dowbridge rotates. Thus, eliminate the reaction forces at the hinge from the equation. Now, the equation, we all know that taking a moment at a point, okay, you resolve the perpendicular distance and we multiply to the force. So over here, when we consider W, it creates a clockwise torque. So as I've stated it over here, torque due to the W. You see, so the torque sign over here, subscript W, is equals to what? The resolved distance, L over 2 cos theta multiplied by the weight. And so that will give us the moment that is happening over there. So where L is the length of the bridge. Then the second one, the horizontal force F creates a counterclockwise torque due to the force. Over here, we're considering the whole length of the rod. So we say that will be, when we resolve that perpendicular distance, will be L sine theta. Then we multiply by the F. You see, so that is how, I put it together. If you look at it, if you take your time and look at it, you will not be fumbling and you will not be in the haze. Nothing will happen. You see that is how it's supposed to be. So take your time and look at this where I've highlighted, mark it around, okay? And see, we just remember we are not going back to GCSE, this A level, and we always know what is called SOCATOA. That will always help us to be able to resolve this. Now, let's come down here. Okay, now here, step 4, the condition given. The drawbridge is rising. What does it mean? It means that the counterclockwise torque must exceed the clockwise torque. As you can see, the values given. So TWF is greater than what? TWW. Okay, so the torque of that, yeah, the clockwise and anti-clockwise. So by substitution into the equation, the respective values given, then we know that TF sine theta is greater than WL2 cos theta as we derive from here. Okay, so we just go take these ones and substitute it back into the 4th condition. Okay, now after that, what do we have to do? We have to take the respective values given, 6,000 newtons, and W, which is 8,000 newtons. And when we put in that, you see, 8,000, 2, we divide it, and we have 4,000. Then we cancel 1,000 from each side. Then, and also divide by 2. Then we have 3 sine theta is greater than 2 cos theta. For sure, we have to divide both sides by cos theta. Okay, so when we do that, we have 3 sine theta is greater than 2. You see, so the sine theta equals the sine theta over cos theta. Then we divide both sides by 3. So the sine theta over cos theta will be greater than 2 over 3. See? Here. And we know that when sine theta over cos theta gives us tan, and that gives us tan theta over here. And tan theta will be greater than 3 over 2. So as I said, it's nothing new. We are not reinventing the wheel. Class, you look at it very carefully. Go up. I'm going to scroll it up, and I'll come down. I'll come down slowly as you read through the question. Okay, then you analyze from the first point of the question. Then we come to the forces, which is the step 2. You see, as I said earlier, there are 3 forces acting on the bridge. Okay, as you can see. Then in step 3, set up the torque equations. Okay, and that is the first time the perpendicular distance. You always remember your SOCATOA, yeah. And a step 4, condition for rising. Okay, the drawbridge is rising, meaning the counterclockwise force must exceed the clockwise force. Okay, then by substituting in the respective value into the equation, we have FL sine theta greater than WL over 2 cos theta. The L will cancel each, so we will end up, having this equation, and we'll substitute all the necessary values given, and there we are. As the Latin will say, quadro esquadromantum, that QED, as it has been proved. Class, I'm going to leave you guys here in peace. Go out there and look at it. If you don't understand, you can give me a call, you can email me, or you can come to my office. Thank you very much for your time. Bye-bye.